All right, so let's talk about section 4.3. In section 4.3, we're going to look at subspaces now of vector space. So in previous section, remember I just kind of went rapid fire through sections 1 and 2. But in section 4.2, we defined a vector space again to be a space made up of vectors where those 10 properties hold. 5 of those properties involve addition, 5 of those involve the scalar multiplication. So a subspace is simply a subset of a larger space. So what is the definition of a subspace right in here? The definition reads a non-empty subset, and your book calls it W, other books may call it S for subset. These are just dummy names, right? So let's say a subset W of a vector space. It's called that when W is a vector space. It says under the operation of addition and scalar multiplication. Okay. Now, when the definitions reads a non-empty subset, so what does it mean when we say a subset, a non-empty subset? A non-empty subset, that means W has the zero vector in it. So that's what the non-empty would imply. It means it has at least the zero vector in it. So that would make it a non-empty subset. Okay. And then of course it has W is a vector space under operation addition and scalar multiplication. Okay. So W therefore is a subset of the vector space V. Okay, under the operations that is defined in a vector space V. Okay, now these two operations, addition and scalar multiplication, these two operations, these simply ensure that the subspace, that's W, remains a vector space itself. Okay. Now, we're going to come to a theorem pretty soon, which basically will state that. Now, where does the zero, by the way, of this W subset come from, non-empty set? The zero, because subset W is made up of vector space V. We just, let's say, select a portion of it, for instance. So that is what we say inherited. That zero vector is inherited from V. Okay. And in fact, all operations defined on W are the same as the ones that are defined in vector space V. So however we define these operations in vector space V, they are exactly defined the same way in the subspace. Think of vector space V as the parent vector space. W, the subset, would be the child. So the child inherits from the parents, and that's what W is. Now, inheriting, it literally means that. It means a lot of these operations in vector space V are inherited to W. Now, some operations are not actually inherited, and we'll talk more about that inheritance in a few minutes. So keep in mind that W here inherits all of the axioms that we talked about of a vector space. And but let me clarify it. Remember, we had 10 axioms, right? 5 for addition, 5 for scalar multiplication. It inherits all of them except two. And I'll show you which ones it does not inherit that we have to verify ourselves. Okay. So therefore, it is sufficient to only test for closure to establish the non-empty set of V, W in this case, as a subspace. Okay, remember, we have 10 axioms. 8 of those 10 axioms are inherited, 2 of them are not. And here in this paragraph, he talks about the inheritance from a larger vector space. So here is theorem 4.5 does a test for a subspace. So again, if W is non-empty subset, remember that means it has at least the zero vector in it. So if W is non-empty, and W is a subspace of V if and only if the following closure holds. Okay. And this one, I will actually prove and tell you more about this in a moment, although the proof is in the book, but I'll show you a slightly different version of it. Now, let's see. So to test to see whether a subset of V is a vector space, all we have to do is do number one and number two. Remember, non-empty means zero. Zero is what is inherited. So first, the sum U plus V have to be in W. That means there has to be closure under addition, and the subset must be closed under scalar multiplication. Now, let me show you why we need to test this, and then I will prove this for you. So I'm going to switch here. Let me switch my share with you. And where is it? Oh, okay, share. I'm going to switch to my OQCam here. All right. And let me turn the light on. Good, so you can see better. Now, here's why we need to test addition and scalar multiplication. So suppose I have the following. Let's say I have this is vector U, and this is vector whatever, V. And this would be the sum vector. It's going to look like that, right? That's going to be the sum vector, U plus V. Now, my, what do you call it? My subspace W. I'm just creating my subspace here. So there you go. This would be W, my subspace. And you can see that in this case, although vectors U and V are in W, but the sum, you see how it extends outside of W? So the sum vector, there's no guarantee that the sum vector is going to be in that space. So that's why we need to test and make sure that W is big enough, if you will, to hold the sum. When it comes to scalar multiplication, so for example, this is V, I can go a constant multiple, call it C, scalar multiple of V. And as you can see, scalar multiple of V now also extends beyond W. So it's for this reason that we have to test, make sure the vector space, the subspace, actually is closed under addition and scalar multiplication. Now, both of these, U plus V, CV, these belong to actually the parent. See, the parent can handle this. This would be the vector space V. Because remember, we're taking a subset from V. And we already proved, let's say, V is a vector space because it has all 10 axioms, 2 of which was closure under addition and closure under scalar multiplication. So V is fine. The question is, does W hold those 2 operations? Okay. Now, let's prove this theorem. Okay, so this is theorem 4.5. The first part is a straightforward. It's the second part that I really want you to see how it's done. The first part says that, and let me read it. This says if W is a non-empty subset of V, then W is a subspace of V if and only if the following closure holds. So if U and V are in W, then the sum U plus V is also in W. Again, this is the closure under addition. And in part two of that, we say that if U is a subset, again, vector U, vector V, as long as you have a vector. I'm following the book's theorem. If U is in W, then C, which is a scalar, C is a scalar, then scalar multiple of U is also in W. Now, for the proof, because the theorem is in the form of if and only if. So anytime we have if and only if, we need to prove these in two directions, one from left to right and then from right to left. So the proof going from left to right is like this. Well, if W is a subspace, if it is a subspace of V, then W is a vector space, right? If we know that it is a subspace of V, then W is a vector space, right? Then W is a vector space. And by that, it means it meets the definition of a vector space, so it meets all 10 axioms. Okay, and I'm just going to say it meets 10 axioms. Okay, therefore, if it meets it, therefore it must be closed under addition, because two of those axioms of 10 was closure under addition and scalar multiplication. So it must be closed under addition and scalar multiplication. So this is kind of the wimpy part of it, right? And this, let me just say, this is due to inheritance. Again, our supposition here is that W is a subspace. If it is, then it has to meet all 10 axioms, two of which are closure under addition, and the other one is scalar multiplication, these two. Now, going the other direction. So what if it's not a subspace? And this time we simply say, well, suppose, let's say it's closed under addition. Suppose W is closed under addition. If it's closed under addition, and let's say addition and scalar multiplication. In other words, number 1 and 2, we're going to say, let's say these two hold. If these two hold, therefore, W must be a subspace. So if W is closed under addition and scalar multiplication, again, we take that as to be a fact. Well, the fact that it's closed under addition, this one is axiom 1 of those 10 axioms. That means U plus V is in W. Okay. And closure under scalar multiplication. This one would be axiom of the 6 of those 10 axioms. This is axiom number 6 that tells us CU is also in W. Okay. So based on this, therefore, you can say thus, any vector, let's say U, V, and W, these three vectors will be in W and also in the parent vector space V. Now, the axioms, we're going to look at the other axioms. Number two, the axiom number 2 was the commutative property of addition. Therefore, U plus V is going to be V plus U because it's closed under addition. And changing the order doesn't matter. This is the one operation that is inherited. This is inherited from the parent. Axiom 3, which is U plus V plus W. This one also holds because this operation is also inherited. The associativity is also inherited from the parent. The other one that's inherited, number 7. Number 7 was the scalar distribution to the sum of two vectors. Okay, so that's going to be Cu plus Cv. This one is inherited. Axiom number 8, this one is simply the sum of two constants or scalars times u. C plus d gives you another constant, right? C plus d is another constant, so we can simply distribute that. All of the ones I'm writing, folks, these axioms right now, 2, 3, 7, 8, number 9, all of these are inherited from the parent. CDU is CD times U. And finally, number 10 is 1, scalar 1 times U is also equals U. Okay. Now, again, these axioms apply to all elements of the parent vector space, V, all of these, including those in W. So these are all satisfied. Now, the ones that are missing here, you can tell which ones are missing. Our assumption is that closure under addition, right? Remember this one. This is axiom 1. This was axiom 6. Now, I have axiom 2, 3. So let's see. Let me go in order. I got 1, 2, 3. I don't have 4. I don't have 5. I have 6, 7, 8, 9, 10. So far, 8 of the axioms are satisfied. The 2 that are missing are axioms 4 and 5. Okay. Now, we're gonna show that these axioms are also going to work with W, the subspace. Okay. Now, because W is closed under addition, remember that was our supposition here, right? Right in here. We are doing the proof going from right to left. So here we said, suppose W is closed under addition, scalar multiplication. Well, because of these two, the fact that it's closed under addition and scalar multiplication, then we can say that for any vector U that is in W now. And if scalar 0 is also in W because all these scalars are inherited, right, from the parent. So those are in W. Therefore, C times U, C is 0. That's inherited. If the constant is 0, then Cu, remember that was one of the properties we had earlier, that gives you the 0 vector, correct? So if the 0 vector is there, which we knew it was there because it was inherited, but if that's another way to show it, if the 0 vector is there, thus I can add U plus 0 vector because we show the existence of it, and that gives me U, correct? And this is exactly axiom 4. Okay, so axiom 4, therefore, is satisfied. We just need to show one more axiom is satisfied, and then W becomes a subspace of V. Now, this scalar C is 0. I'm going to let scalar C be -1. And when we multiply -1 times U from earlier work, previous section, we said that's negative of U. And this is going to be in W, right? So, and why this is due to axiom 6, right? This is as a consequence of axiom 6, which is this one. You see that CU is in W. I'm letting C be -1. Okay. And so if that is true, thus we can say, sorry, thus. So negative of U is in there. Therefore, it is possible to add U plus negative of U because it exists. It's in W. And we know that, again, U is in W, negative of U we just showed is in W, and the sum of those two from previous section has to be the zero vector. And this is indeed axiom number 5. So axiom 5 is also satisfied. Therefore, W forms a subspace. So make a long story short, folks, in order to show that W is a subspace, a whole bunch of these axioms are inherited, right? All of these are inherited. We don't need to show these. The only one we need to show is closure under addition and closure under scalar multiplication. And then we say, okay, yeah, this is good. That's a subset. Is everyone okay, by the way? Any questions, ladies and gentlemen? No questions? Okay. Now I know it's like, can we see some examples? So let's do that. Let's actually look at a few examples here. So the first example, this is example in section 4.3. And let's say W is just my subspace is made up of only the zero vector. It has nothing, no other vectors. I handpicked and I just made that one. Remember the parent has zero in it. So I just say, you know what? I'm just going to borrow the zero from the parent, and that's now my subspace. Well, this one is a subspace. W is a subspace of V. It meets, if you want to show this meets all 10 axioms. And indeed, this is called a zero subspace. Now, you would want to say, well, what good is this for, right? It really isn't hardly any good at all. We can't use it. But just to want to show you that this is an example of a subspace. This one is called a trivial, indeed. That's what it is. It's like trivial solution to homogeneous systems, right? 0, 0, 0 works in every homogeneous system. We don't use it. We want other than zero solutions. Same thing with this one. This subspace isn't going to do me any good. So that subspace is called a trivial subspace. The trivial subspaces are improper. So some call this an improper subspace. We would like to have proper subspaces. So that's one example. Another example, the parent itself. What if I copy the vector space V onto itself? It's like duplicating a file, folks. Like you create two versions of the same file. So V is a subspace. Every vector space is a subspace of itself. This is also the trivial, folks. V is a subspace of itself. Again, these two, I'm just showing you examples. These are really not going to do anything for us. This one is also trivial or improper. Okay. Now, subspaces other than trivial, we call them proper. Let me just put the notes for that one. Subspaces other than trivial are called proper subspaces. Okay, proper subspaces. All right. Now, let me switch to the book. And again, I promise you folks, we're going to see a lot of cool, nice exercises in a few minutes to really clarify what we're doing here. But let me change my share of what we're looking at here. I'm going to change my share. I'm going to go back to the book. And okay. So that's theorem 4.5. Now let's go to, and the book has its own examples. We'll look at the exercises and this will clarify it for you. Now, here's interesting. For instance, example 5, they're looking at subspace of functions in calculus, it says. So notice here, W5 here is the vector space of all functions on 0, 1. So this is really V. In our theorems, we have capital V. That's what that is. That's your capital V. This is the parent that holds all functions defined on 0 to 1. Now, and then he's selecting 4 different subspaces. This is just the author. He says, you know what? I'm going to look at polynomial function. Well, polynomial functions are subset of functions, right? As long as everything is in 0 to 1, 0 to 1, 0 to 1, we're good. So, polynomial functions are functions, right? So it makes sense W2 is a subset of the larger W5. I mean, W1. What's W2? He says, well, I want W to be the set of all functions that are differentiable. Okay, well, polynomial functions are differentiable, correct? That's from calculus. We learned in Calc 1 that polynomial functions are all differentiable. Therefore, they are subset of all differentiable functions. Now, there are functions that are not differentiable. Those will be outside of W2. But we're talking about W1. Only polynomial functions, that circle of W1 is within W2. Okay. And then he defines W3 to be functions that are continuous. Well, all differentiable functions have to be continuous. So if you grab a continuous function, for example, from that space, then that function will be differentiable. Okay. And W4, the set of all functions that are integrable. Integrable functions are subset of functions. But not every function is integrable, correct? That would be outside of W4. It's in W5, but it's not in W4. Now, look at, by the way, W3 and W4. Continuous functions and integrable functions. So there are, again, continuous functions that are integrable, but not every integrable function is continuous, right? So that's why W4 is larger than W3. Look at W3, W2. I'm going inside one layer at a time. W3, W2. Remember in calculus, we said that if a function is differentiable, W2, it has to be continuous. Remember that work? That's from Calc 1. Differentiability implies continuity. So differentiable functions are within the class of continuous function. Now, is every continuous function differentiable? What do you think? Is every continuous function differentiable?
Nope.
No. Very good. Thank you. It's not. And remember, for example, we could have a continuous function, and at some point there could be a cusp, a corner point, or a vertical tangent. And at those points, the function is not differentiable, but it's continuous. For example, the absolute value function, right? The absolute value function is continuous. I'm talking absolute value of x. But it's not differentiable at 0. So this makes sense. So if the function is differentiable, it's continuous. But outside of this green oval, not every continuous function is differentiable. And there you go. So that's the idea of, again, subspaces. Yeah, we'll do our own in just a moment. Let's take a look at this next theorem. This theorem, 4.6, by the way, it's going to be the last theorem. Then we'll be able to look at some examples. Theorem 4.6, simple theorem. The theorem says that the intersection of two subspaces, let's see, if V and W are both subspaces of vector space U. Now, remember here, U becomes the parent, because V and W are subspace of it. So U is the parent, V and W are the children. So suppose you have two subspaces from U. The intersection of V and W, which is in the Venn diagram you see, is also a subspace. And there you have the Venn diagram for it. So the parent has a whole bunch of vectors in them. It's a vector space. That means every vector, all the vectors in U, the circle of U, meet those 10 axioms. Now, and then we have these two children. The two children, the intersection of the two will also, if V is a subspace, the circle of V, the circle of W, the intersection, the green area, would also be a subspace. Okay. And there you go. Let me, we'll do our own in just a moment. You're welcome to look at these. Okay. So now I'm going to do some examples here with you, for you. So let me go back to my, I'm going to change my share. And let me go back to my OQ Cam. All right. So we're going to actually see some examples here. All right. And again, if you have any question about these examples, folks, please ask. Let's begin with this example. We're going to see a bunch of them. So for this example, see, so I made up W. Okay. W is the set of all vectors that are in this form, ST0. Notice this is like a custom-made vector, where S and T are real, just real numbers, any number you want them to be. This set is a subspace of R cubed. Now remember, R cubed, that means 3-dimension, in 3-dimension. So how do I show, let me just put in front of it, show that this is a subspace? How's that? So please add the word show on yours as well. So I need to show this. Now, anyone remembers what I need to show for a subspace W to make sure W is a subspace of V? In here, by the way, your R cubed, this is what the parent is. This is V. We want to show that what I have made here is a subset of that. Now remember, for example, in R cubed, the vectors will have 3 components, right? Remember, in vector form, we write it like this. Let's say it's in the form S, STU. Isn't that how the vectors in 3D in R3 look like, STU? That's the most general form. I'm actually being creative here. I'm going to say, you know what? I'm only going to look at the vectors. This is, and there are infinitely vectors like this. Like, for example, I could have 1, 2, 4, 7, 0, 9. So there you go. I'm being creative. I'm making a vector here that is in this form. It's in the form st. But my third component, I always want it to be 0. Is that too much to ask? Isn't 0 one of the real numbers that's in R3 as part of the STU, one of the last component? Remember, STU, these are real numbers because you're in R3. U could be any real number. I'm just interested in the ones with 0. That's all I care about. I don't want the other ones, infinitely many other U values. So, what do I need to show in order to show that this is a subspace of V? Anyone remembers?
You need to show that W is closed under addition and scalar multiplication.
Very good. Thank you. I need to
I
show.
I had
Yeah,
another question, Professor. Sorry.
yeah, sure. Go ahead.
Say that you wanted to structure this as like a legitimate like proof. Would you would you prove both of those things that it's closed under scalar addition and multiplication? And would you also have to show that every vector in W is in V?
No, you don't have to do that. That's why, remember, we mentioned the reason we don't have to do that is because those other ones, let me,
They're inherited.
exactly, those are
Okay.
inherited. So there you go. These are all inherited right in here.
But if we don't know that it's a subspace yet, how do we know that they're inherited?
Oh, oh, the moment that you create a subspace, those are automatically inherited.
But aren't we proving that it's a subspace?
Right, inherited, but the question is, uh, will these operations, are these valid operations? Can I
Okay,
do this and can I do that one?
got it.
Yeah, we have to show these two. And also there is a third one, remember, which was inherited, the 0, right? 0 is inherited from V.
Hmm.
So usually those are the three things that we do. 0 is in there. And then again, 0 would be because that's part of V. V would not be a vector space without the 0. So that's inherited. But the
Okay.
sum and scalar multiplication is not necessarily inherited.
So we're assuming essentially that W is in a way like contained within V. We just have to prove that it's a vector space.
Exactly.
Okay,
Exactly.
got
Yes.
it.
And remember, in the beginning, we mentioned that W is actually inside. It's a vector space inside another vector space.
Okay, understood.
Yeah,
Thank
thank
you.
you for asking. I appreciate it. Thank you. All right. Okay. So the only things we got to do is, again, we got to show that it is closed under addition and scalar multiplication. Just that, just those two. So let's go ahead and do this. So I'm going to grab two vectors from this list. Remember, W has infinitely many vectors like that. So we're going to handpick two of them, U and V. And we want them in the general form, by the way, folks. So I'm not going to say, oh, I'm going to go 2, 5, 0, 10, 1000, 0. We want to keep it general. So isn't U going to be in this form, S1, T1, 0, right? Remember, my vector is going to look like this, right? That's my U. Vector V is going to have its own constant, right? Its own first component, its own second component, and the third component must be 0, right? So there you go. And let's add two vectors. And how do we add vectors? We add each component of the vector. So S1 plus S2, T1 plus T2, 0 plus 0, and there you go. Of course, 0 plus 0 is just 0. Now, S1, remember, S and T, I have it up here. S and T are real numbers. So when you add two real numbers, we get a real number, correct? This becomes like the new S. So that's going to be there. I'm just going to keep it as S1 plus S2. T1 plus T2, I'm just copying that. And 0 scalar plus 0 is 0. And look at the structure of this. this structure, look at that one, and look at this one. Do they not have the same structure? This one is a real number 0, and we just showed that the sum of any two vectors will be in the form of real 0. Therefore, this is closed under addition. And now I feel good. I say, oh, good. So if I, for example, if I want to do 1,000 plus 1,000,000 0 and add it to, I don't know, 500, 5 million, whatever crazy number I'm going. There you go, 5,000,000 0. I'm not worried that, will I be able to do this operation? Sure, because we showed closure. In other words, there you go, 1,000 plus 500. You're guaranteed 1,500 will be there for the sum. 5 million plus 1 million, you're guaranteed 6 million. You're not going to run out of that number. You're going to have the number there, and 0, 0 is 0. So, for example, I can do operation like this now. That's what closure means. Means if you add two vectors, you're guaranteed that the resultant vector will be there. The sum vector will be there. So we showed closure under addition. Is everyone okay with this part of it? And then, okay, so if you're good, now let's show close under scalar multiplication. C is a scalar. U is the vector. So what does CU look like? Remember, here's my U. So CU is in the form CS1T1 0. And again, the way the constant multiplies by a vector, it multiplies by every component of the vector. So this is going to be CS1, CT1, and C times 0 is 0. And there you go. So C is a scalar. S, real number, think of it as a scalar. You have product of two real numbers, which is a real number. CT1, that's a real number times real number. The product will be another real number. And of course, see, the 0 doesn't change. So every vector I grab from this subspace, the third component, it will have just 0 in it. That's not going to change. So we just showed that this is closed under scalar multiplication. Right, and of course, just for reference, I'm going to say the 0 vector definitely is in W. This is inherited from the parent, from this, because 0 is in R3, isn't it? The origin of the coordinate system, X, Y, Z, isn't it 0, 0, 0? So that is a 0 vector. There you go, in R3. Isn't that the 0 vector in R3? So that is inherited. See, I have it in here. I could have 0, 0, and 0. That's when S and T are 0. So everyone okay on this one example? All right. So let's take a look at another example. Now, this is actually kind of like an extended example. I'm going to create like 3 examples that in line with one another. Let's check this out. I think you're going to like this one. So let's say we want to know whether this planes, I'm looking at planes, that means R2. We're looking at planes through the origin. Planes through the origin. All planes through the origin are subspaces of R3. That would be another example. The subspace is here, all planes through the origin. So this is your W. subspace of R cubed. This is your V. Here's your W. Now, if I look at the geometry of this, so let's say here I have my X, Y, Z coordinate system. X, Y, Z. And I'm looking at the planes through the origin. Now remember, these planes go infinitely in all directions, right? So I'm just looking at portion of a plane that runs through the origin. Okay, and suppose this is vector u, and this is vector v. Remember, this plane goes in that direction forever, in this direction forever, in all directions. So you're looking at just a portion of that plane. So u plus v is going to be in there. Okay, so there you go. This is u plus v. That means it's closed under addition. Now you might want to say, well, can you draw it outside? Sure. Let's say this is u plus v. But then remember, my plane is only portion. So I'm going to adjust my plane because planes through the origin go in all directions, right? There you go. You see what I mean now? So don't worry, like, well, what if that thing goes outside of that? Then I'm going to extend my plane. The plane is adjustable here. Okay. And there you go. So here's my U now, and here's my V. So that's the sum. Now, let's look at the scalar multiple of one of them. Let's say CU here. If you get a scalar multiple of U, this would be CU, wouldn't it? That would be in the plane also. Now, again, you may say, well, can you make this come outside of the plane? Sure, but then I'm going to enlarge my plane. Remember, this is just zoomed in. The plane goes in all directions forever. What's important, folks, here is through the origin. Now, the origin is at 0, 0, 0, isn't it? So isn't the zero vector part of this plane because it runs through the origin? So 0 is there. That means this subspace is closed. It's non-empty because at least I can have a zero vector, right? 0 is in W. Zero vector, that is. So that means it is non-empty. It's non-empty. And then I just showed you it's closed under addition and scalar multiplication. Geometrically, I showed that one, right? U plus V is in there, is in W. And scalar multiple of either U or V, doesn't matter, is in W. So we have all three. We have a non-empty subset, close under, this is closure. Both of these are closure and closure. This is for addition, and this is a scalar multiplication. Therefore, that is a subspace. Is everyone okay on this work? All right, let's take a look at another example like this. Again, we're going to stay on this example. The next three examples are actually continuation of this, but I'll make it more analytical, not geometrical. So let's now talk about, how about lines? You tell me. How about lines through the origin? Are these a subspace of R cubed? The lines through the origin. So again, for example, here's the 3D, R3. A line through the origin. So for instance, it could be a line like this. There you go. That's a line through the origin, L. Will that be all lines that run through the origin? That's one of them. I could have infinitely many lines drawn, right? So what do you think? Are these lines, do they form subspace of R cubed? So all lines through, indeed, they are subspaces of R cubed. The key here, folks, by the way, the key word is origin. When we say through the origin, if I change the verbiage here, take the origin out, then it's no longer. Because I could draw a line here. And if I draw a line here, it doesn't go through the origin, that means it doesn't inherit the zero, right? There is no zero on that line. It has to be through the origin to make sure that the set is non-empty. So for this one, again, the zero is there. And again, there you go. Here's my three-dimensional. I already drew a line, but just to show you one more, I could have a line that goes like this. There you go. Here's my line L, right? X, Y, and Z. The key is that zero is there. And now you can also see if you have a vector, for instance, this is vector U, and this is vector V. Would you agree that the sum of these two vectors lies along this line, right? So this is my set W. Again, zero is in W. Sum of two vectors be in W, and the scalar multiple will be in W. For example, if this is U, 5 times U will be there. You just extend that because the line goes forever, right? In both directions. So any scalar multiple of U will lie on that line. So that's going to be okay. Again, on both of these, remove the word origin, and these suddenly are not. They're not subspaces. So they have to run through the origin. We're good, everyone? Okay, now let's take a look at a continuation, again, working with the same ideas. And by the way, since we talked about lines and planes through the origin, let me write this for you. The only subspaces of R cubed, 3-dimension, the only subspaces, zero is a subspace. Remember, zero is a subspace of any space, right? That's the trivial subspace. That's one, the trivial subspaces of R cubed. The next one would be all lines we just showed geometrically through the origin. Next, it would be all planes. We showed both of these geometrically, all planes through the origin. And what was the other trivial? Anyone remembers? We had two trivial subspaces. Zero was one of them. What was the other one?
The space itself.
Very good. Thank you. R cubed itself. The space itself is a subspace of itself. Remember, these two are trivial. So those are the only subspace of R cubed. Isn't that cool? Now to show you an example, let's say, for example, can I say the general form R2 is a subspace of R3? Can I make that statement without any conditions?
Isn't R2 just a plane through the origin? So yes,
Now remember, if it's through the origin, but I'm removing the origin out of this one, I'm making it general.
then no.
All planes are subspace of R cubed. So in other words, do all planes go through the origin? Not necessarily, right? You could have a plane that's parallel to the XZ plane or the XY plane, couldn't we? So they don't necessarily go through the origin. Up here, we said that the keyword is origin, and it's yes. These are the only subspaces. So this one, the answer is no. R2 is not a subspace of R cubed. Again, because, for example, R2, for one thing, R2, isn't it just two components, whereas R3 has A, B, C? So it cannot be. It cannot be. And in terms of the geometry of this, R2 are set of planes in R3. Well, not every plane runs through the origin. That's another geometric argument for it. So this is not. Therefore, let's see what subspaces of R2 are. The only subspaces of R2 are, what do you think the first one is? We just did only subspaces of R3. What do you think the only subspace of R cubed is? First one, the trivial, right? A zero is a subspace of any Rn. Okay. And what do you think in terms of what you see up here? Try to make this work with in R2. Remember, R3 is 3 dimensions, so lines and planes have 1 less dimension for planes, 2 less for lines. R2, what would be, when you reduce R2 to R1, what do we get?
Lines through the origin.
You got it. Lines through the origin. Okay, and what's the other one? The trivial, R2 itself. The plane, every plane is a subset of R2. Whether they run through the origin or not, it doesn't matter. R2 can handle any plane. Okay, now let's take a look at again. Now I'll show you these with numbers. Okay. So here's our next example. Let's say I have a homogeneous system. 1, 2, 3, -2, -4, -6, 3, 6, 9. And here I have x, y, z equals 0, 0, 0. And you will see in a moment how this will relate to what we just have done. So this is a homogeneous system, agreed, because it's set equal to 0. Now, if you go through either yourself or go through Gauss-Jordan or just simply make an observation, if you look at this, the way I made this one, if you multiply the first row by 2, don't you get the second row? That's what this one is. Multiply first row by 2, you get this one. Multiply first row by 3, and you get this one. True? So if you go to Gauss-Jordan on this one, our Gauss-Jordan is going to look like what? 1 minus 2, 3. Because this second and the third row are simply a constant multiple of the one above. So this is the Gauss-Jordan form of this. Now, so what would the solution look like? The solution, remember, this is equal to 0, 0, 0 here, right? I have 0, 0, 0. So my free variables are y and z here, correct? Y, z, and x1, or I'm sorry, x is in terms of my free variables. So in other words, I'm going to let z be t, let y be s, just like the one you did on the exam. Those are my free variables. And with that choice, isn't x 2s minus 3t? Move 3 to the other side, becomes -3. -2 to the other side. Because remember, this first equation, doesn't it read x minus 2y plus 3z equals 0? That's what the first row reads, right? Because it's homogeneous system, we didn't write 0, 0, 0 here. So here is what I have. Now, therefore, my my solution looks like this. X is 2s minus 3t. Y is s and z is t. Okay. Now, and this comes from your calculus, the third semester calculus. In third semester calculus, we know these, we recognize these, this parametric form. This is the equation of a plane. This is equation of a plane. That's what that is. Through the origin. Through the origin. This is from Calc 3. Okay, so we have the equation of a plane through the origin. And some of you probably recognize this one, x negative 2y plus 3z. And taking you back to your Calc 3, the coefficient on these variables give you the normal vector, right? The normal vector is 1 minus 2, 3. So you have the equation of a normal vector to the plane. Remember, to equation of every plane, we need to have a normal vector. And there you go. And the points, we can get them from the equation. As long as we have a point and a normal vector, we have the equation of a plane. So there you go. This is a plane through the origin, isn't it? So the solution space, that's what this is. X, Y, Z. This is called the solution space. The solution space is a subset of the homogeneous system, is a subspace of R cubed. It's a plane through the origin. And remember, previous example or examples, we said all planes through the origin are subspaces of R cubed. So here's an example of a system that generates that plane. Okay, let's take, is any question, by the way, on this, folks? Are we okay on this work? I'll do another one. These will be quicker. Next example, if you're good on that one, let's take a look at our next example. And in this next example, sorry. Okay, so for this next example, let's take a look at this one. Suppose now I have a system of equations. It's 1, negative 3, 4, negative 2, 7, 1, 3, negative 8, 2. And then I have x, y, and z, and that's equal to 0, 0, 0. Again, it's a homogeneous system. Now, I went through Symbolab and did Gauss-Jordan on this one. If you do Gauss-Jordan, then we're going to get the following. We're going to get 1, 0, 0, negative 2, 1, 0, 3, 1, negative 19, 0, 0, 0. Okay. Now, what does the third equation tell us? 0x, 0y, negative 19z is 0. True. So that means z is 0. Plug z back into here. Z 0. If that's 0, then y is 0. When you back substitute, y is 0. Plug x and y, 0 and, I'm sorry, plug y and z. That's 0 here, 0. Z, this is y. 0, 0. X must be 0 with back substitution. Now, what is the solution set here? Isn't the solution set 0, 0, 0? That's the only solution, right? The trivial solution. And this is equal to the zero vector in R3. And there you go. Therefore, the solution space is indeed, which is, again, we said this is the trivial subspace to every space. So we just showed that this is true with an example. Okay. And that's probably good enough. So are we okay on this one, folks?
Yeah.
Okay, fantastic. Now, let's see. Let's take a look at actually some exercises from the book here, and then we got 5 minutes because we usually take our break at 7:40, I think. Is that correct, or am I dreaming here? Right, 7:40 is when we usually take the break.
It's about right.
Okay, thank you. So we got about 5 minutes to do an example. Now, let me mention for that 5 minutes, this is worthwhile, folks. So I'm just going to write here, these are, because we talked about inheritance, right? So we're looking at properties in V, and this is not an exhaustive list I'm writing, okay? That may not, these may not be inherited. Remember, those 8 axioms are inherited. So what are some of the things that are not inherited other than the scalar multiplication and the addition, right? We talked about. So these are the things that are not necessarily inherited. The norm of a vector is not inherited. And we're talking about, this is everything that I'm listing is in V. It's in V. That may not be in and not inherited means not in W. Okay, so the norm of a vector, and anyone remember what the norm of a vector is? The norm of a vector. The norm of a vector is the magnitude of the vector. So for example, V may have a vector, here an example of a norm. So let's say I want to find norm of U. Okay, norm U. And suppose my vector U is, this is my vector U, 1, 2. The norm of the vector is the square root of the sum of squares. So the norm of this vector is the square root of 5. This is not inherited. And the reason is because, remember, U plus V may not be in W. If U plus V is not in W, then the sum of that, the norm is going to exceed the length of the vector that's in W. So that may not be inherited. The other thing that's not inherited is the inner product space. Now, inner product space, this would be in chapter 5. We talk about those. Those are not inherited. And also some of the things about this, usually W, the subspace has a lower dimension. It has lower dimension than V. The basis is not inherited, the basis of a vector. And we define the basis later on in chapter 5. Okay. And then there are some topological vector spaces. Okay. So let me just say topological. You could research on this if you like to yourself. Okay. But some of the topological vector spaces are not inherited. An example of these, you may have heard of these topological vector spaces. I'm not sure if anyone's heard of Banach vector spaces and Hilbert. So these are not inherited again. Okay. Oh, and let's see, the basis, actually, we'll look at the basis in not chapter 5, sorry, it's chapter 4, section 5. So we'll look at that. I'll do the video on that for that. Remember, next week we don't have class, but I'll do a video on that. So these are just the things I want to show you, that what is not inherited. So operations that are specific to vector space V may not be inherited in W. So if they ask, well, is this operation, for instance, in W, we have to show that it is. Okay. All right. Now, we are right at where we need to be for our break. So if it's okay with everyone, I'm going to first pause the recording here. Okay, and all right, so we're going to do exercise number 4. So I'm going to write it down, number 4. This is in section 4.3. And exercise number 4, it says W, remember the subset, is the set of all 3x2 matrices of the form. I'm going to write the form as A plus B, 0, B, 0, C. Okay. And the vector space where this is selected from is the set of all matrices 3x2. Okay, now let me change my share so you see what I have written. And let me see. Okay, so I'm going to share my camera with you. All right. So here's what number 4 is. Now remember, again, the vector space here, the set of all 3x2 matrices look like this: A, B, C, D, E, F, where these are real numbers. So this is just the author. The author says, I want 0 here, I want 0 here. I just want a number. And then this element in the second row, first column, I want it to be the sum of these two. That's what I want. So let's see if that selection constitutes a subspace. So first of all, is the set W, so this is W, is W non-empty? The first question. W is non-empty. So what should I show that it is not empty? Remember, the non-empty had to do with a 0. In the case of a vector, 0 vector, now we have to look at in terms of a 0 matrix, a matrix of zeros. So in other words, 0, 0, 0, 0, 0, 0. Will this work? This is the case where A equal B equals 0, right? So remember, A, B are real numbers in the general vector space here. So if I let A be 0, B be 0, isn't 0 plus 0, 0 for the second row, first column? So that's this one, 0 plus 0. If you want, you're welcome to write it. There you go. Here's my A, here's my B, here's A plus B, 0, 0, and let C be 0 also, right? And therefore, W is non-empty. So that's good. The 0, the 3x2 0 is there. Now, remember, we need to check only two things. Is W closed under addition, and is W closed under scalar multiplication? Okay, and let me, good. I want to make sure my microphone was on. I wasn't sure. It is. All right. So we're going to show closure under addition if it happens. So I'm going to write, this is one such matrix selected from what author has in mind. So I'm going to get a matrix from his toolbox of matrices of this form. And there you go. This is in W, correct? Because I made sure that I have an element here, A, an element here, And this, I'm going to make it the sum of these two. Now, let's look at the second one. The second one will have the same structure, right? So I have these two numbers. Like this could be 5, that could be 10. What's important that in second row first column, it's going to be the sum of those. A2 plus B2, 0, 0, and this is going to be some C2. This is also in W. Again, I grab these two without specific numbers. The general form, I grab them from the author's subspace. Okay, now let's see. Let's do their sum. Their sum. So if you like, you're welcome to call this like, I don't know, M prime, M double prime, M1, M2, whatever you want to call those matrices, it doesn't matter. So let's do their sum. That means we're looking at closure under addition. So for that, how am I going to do this now? We're adding two matrices. Remember, to add matrices, we add elements in the same row, same column. So A1 is going to get added with A2, right? So I'm going to write that. I'm going to have A1 plus A2. First row, second column. B1 gets added with B2. So that's going to be B1 plus B2. Second row, first column. I have A1 plus B1 that adds with A2 plus B2. And when it does, I'm going to put A1 plus A2 plus B1 plus B2. And of course, second row, second column, that's 0, 0. 0 plus 0 is 0. Third row, first column, again, 0 and 0 makes 0. And third row, second column is C1 plus C2. All right, so it looks like if I grab any two matrices from the author's subset, the structure is going to be preserved, isn't it? It's going to have a number here, a number here. The number in the second row, first column is going to be the sum of the top first row, first column plus first row, second column. So looks like that structure is preserved, true? Therefore, the sum is in W. So this operation is closed under addition. Now, let's look at the scalar multiplication. That's the sum. Now we're going to look at scalar multiplication. Is it going to be closed under scalar multiplication? So because he's using A, B, C, I'm not going to use C. Usually we use C for scalar. So next letter I'm going to use would be what? D. Let D be a scalar. If D is a scalar, then let's multiply now D scalar times a matrix that is in the subset. It's going to be in the form A plus B, 0, B, 0, C. And when we multiply D times this matrix, again, matrix multiplication, every element of the matrix is going to be multiplied by D. So D multiplies by A, that's going to be dA. D multiplies by B, it's going to be dB. D multiplies by the binomial, it's going to be dA plus dB. And times 0, anything by 0 is 0. And then D multiplies by C, that's going to be dC. And again, think about the form of this matrix. It is preserved. This matrix looks exactly like all the matrices in W. You have a number, first row, first column, first row, second column. You have a number here, a number here. See, I have a number. What's important here, second row, first column, has to be the sum of the top two. Look at the second row, first column. dA is the sum of that plus that. And that was just through multiplication of D times that. So it looks like everything looks good here. Therefore, W is a subset, isn't it? So that's what the question is. W is a subset of V, a set of all 3x2 matrices. Is everyone okay on this example? Any questions? Now we'll look at another one. Let me switch my share and let's go back to the page of the book. And let's take a look at, how about number 8? Now, in this segment, by the way, these are subsets that are not subset of the vector space that are not subspaces, the question. And 7 through 20, so you got about 13 of these, 14, including 7 itself. Okay. In this segment, W is not. We're told it's not. Now, I guess he wants to say, why is it not? Verify this by giving a specific example that violates the test for a vector space. Theorem 4.5. Remember, closure under addition, closure under scalar multiplication. So it's violating one of those, most likely. Let's take a look at number 8, if that's okay. And we can look at any one of these you want me to. But for now, let's look at number 8 and see why is it not. So I'm going to write this number 8 first of all. W is the set of all vectors in all 2. W is vectors in R2 on a plane, two-dimensional plane, whose second component is 1. Whose second component is 1. Again, of all those vectors in R2 that are in the form AB, he is singling out a specific one. Okay, let's check this out. Going back to my notepad. So here you go. That's what, again, number 8 is. Now in R2, all the vectors, by the way, in R2 are in this form, right? AB. He says, well, I know this is all available to me, but the one I'm going to use, the subspace I'm choosing from this, are the ones whose second component is 1. So one that is tailored to this author's choice, that's going to be A, comma 1. Isn't that what he has in mind? Second component is always 1. So he says again, I'm just going to choose vectors whose second component is 1. First could be whatever. Could be any real number. Let's see, why is this not? So, close under addition or scalar multiplication. Let's look at closure. Under addition. Let's see, sorry, closure. There you go. Okay, so we're looking at closure here. And have it there. Okay, closure under addition. So what am I going to do? Well, we're going to grab 2 vectors from the author's list of vectors. Isn't this one vector? Let's say 3, 1. The second component has to be 1. The first component could be anything again. So how about, I don't know, 10, comma, 1. And let's add them, see what happens. And when we add, what do we get? The first component, 3 plus 10, that would be 13. What will the second component be? Vector addition. I have to add a second component and second component. So now I get a 2, don't I? That's how vectors add, correct? Now look at the second number. This is no longer 1, is it? That's not 1. And therefore, this vector is not going to be in the author's space, the one that he picked. It's not going to be in there. Therefore, it is not closed under addition. Now, how about closure under scalar? And at this point, by the way, that's all we need. So this is not a subspace. And he already told us it's not a subspace. Now, if somebody says, well, I want to try closure under scalar multiplication, let's try this. Again, for the purpose of the exercise, we're done. But let's try scalar, whether it's closed under scalar multiplication. So I'm going to do, let's say 5, that's my scalar. I'm going to multiply by one of the vectors from the author's list of vectors is this one, right? Second component 1. First component, I like number 7, so I pick 7. This vector is going to be in W for sure, because he said he guarantees that they're in this form. Now, when we multiply this, remember multiplying by vector, scalar times vector, you multiply both components. So that's going to be 35, comma 5. Look at the second component. It's no longer 1. So if, remember, all the vectors in his W have only 1 for the second component. So this vector is not gonna, it's not gonna be there. It's not closed. That means there's not gonna be a vector that looks like this. 35 comma 1 will be there. This is guaranteed by his choice. Any number comma 1 will be there, but not if the second number is in 1, you don't have it. It's just not available to us. This is not 1. Another reason. And how about the 0 vector? Is the 0 vector in there? Remember, the 0 vector is going to be 0, 0, right? So there you go. It's not there because he doesn't have that. He says all my vectors have 1 for second components. So this is not in W. So this one definitely not a subspace. Everyone okay on this one, I hope. Let's look at another one. Let me switch. And let me change my share. We're gonna switch to the book. Okay. And again, any one of these you want to look at, please let me know. How about something on 16 through 20? Does anybody care which one you want to look at, or should I just randomly pick one? Any particular one?
Any,
Which one?
any of them work.
Oh, any of them, sure. If any of them, then how about number 20? In number 20, well, let me write it down first. Number 20, W is a set of all vectors in R2. W is in R2, whose second component is the cube of the first. Oh, sorry, the square, not cube. The square of the first. Okay, so the first component, I'm going to call it A. The second is the square of the first. That would be A squared. Okay, let's switch and let's check this one out. Again, the second component is the square of the first. So these are the set of vectors that he has selected. So let's see if this is closed under, first of all, 0. Is 0 in there or not? Let A, B, 0. What will the second component be? 0 also, right? So yeah, 0 is there, no problem. The 0 vector is going to be there. So that's good. Let's see if it's closed under addition. Closed under addition. We want to verify that. Is it closed under addition? So to show that, I need to find two vectors from that subspace. So for example, is it okay if I choose first component 3? Now the second component is going to be 9, right? His vectors in W are going to be in this form. So for example, he doesn't have 3, 7. He doesn't have 3, 8. He doesn't have anything but the square of the first. So 3, 0 is in there, 3, 20 is in there, but 3, 9 will be there. Because remember, your vector space, the parent has all real numbers for the first, all real numbers for the second. He's just being picky. Or I should say selective, not picky. Now, for the second vector, because we're going to add two vectors, see if we maintain the structure. Let's say I pick 4. How's that? You can pick any number you like. Now, the second component has to be 16, right? Remember, these are the only available vectors to us. Now, how do we add two vectors? We add the first components, so it's going to be 3 plus 4. We add the second components. This is just how vector addition is done. The vector addition doesn't care about what author wants, right? It says this is the operation on vectors. So 3 plus 4 would be 7, 9, and 16 would be 25. And what do you think? Is this, can I say this is in W? Will it be? Second component has to be square of the first. Remember, if it's not that, it's not in W. 7 comma 49 would be available to me, but not 7 comma 25. This doesn't equal 7 squared. Therefore, it is not closed under addition. And same thing with scalar multiplication. Let's look at scalar multiplication. For scalar multiplication, let's say I want to do 2 times. Now, you want to call a vector that's in this subset? Anyone care about calling a vector or?
We do 5 and 25.
Thank you. 5, and the second one has to be 25. So 5, 10, we couldn't choose that vector. It's not available to us. We have to choose from what's available. So let's do 2, 5, 25. Thank you for that. And we're going to multiply 2 times 5, we get 10. 2 times 25 would be 50. And look at this one. That doesn't equal to 10 squared, does it? So it's not closed under either of those. Therefore, this is not a subspace. W is not a subspace of R2. And there you go. So hopefully everybody is okay on this one. Let me do one last one and then we can move on to our next section. I hope you find this easy, not challenging, not difficult. Let's go further south. How about
It's a little
number-
abstract for sure.
Okay. Now, in this segment, it says determine whether the set is a subspace of R cubed with standard operations. Okay. Now, let's see what these are now. Standard operation means nothing like this. That's not standard, is it? Where the second row, first column is A plus B. Number 20 we did. That's not standard operation if the second has to be square of the first. So these or have a standard operations on them. Okay, which is addition, multiplication. Now, is it okay, again, any one of those you want me or us to work 37 to 42? How about, I don't know, how about 42, the last one? Let's take a look at number 42. In number 42, W is on the set. First component, remember, this is in R3, so you have vectors that have A, B, C components. So it's 1 over x1, and x3 is whatever x3 is. And it says x1, x3 are real numbers, and x1 cannot be 0. So again, from that infinite list of A, B, C, the components of a vector, he's creating his own types of vectors that he's going to extract from that set. So let's see if that one qualifies. Okay. Let's see if 0 is there first of all. Will 0 be in there? X1 cannot be 0, right? X1, if this cannot be 0, there's no way this will be 0, agreed? So 0 is not in W. Are we okay on that one? We're told x1 may not be 0. Well, the 0 in R3 isn't the 0. That is the 0, right? And he told us x1 cannot be 0. So 0 is not there. So that's enough to kind of say that this is not a subspace. But let's try closure under addition. Let's see if it's closed under addition. To show that one again, closed under addition, I need to grab two vectors from this set. So for instance, I'm going to let x1 be anything you want me to pick, as long as it's not 0. So how about, I don't know, 1/2? x1 is a half. If x1 is a half, what will x2 be? It's 1 over x1, right? It's reciprocal of x1. That means x2 would be 2. See, I have no choice on that one. There's a rule for x2. And x3, it says can be anything, right? I'm going to let x3 be 10 because there's no restriction on that. It just says x3 is real number. So I made 10. Therefore, one vector is a half, 2, and 10. A second vector, I don't know, let x1 be 1/3, whatever you want it to be, as long as it's not 0. How about 3? That would work as long as it's not 0. So I picked x1 to be 3. x2 is reciprocal of that, is 1/3. x3 is any number you want it to be. I'm going to choose 8. Let's add these two. Now, the way we add them again is like you always add two vectors. You add first components, second components, last. A half plus 3 is 3.5. 2 plus a third is 2 1/3. And 10 plus 8 is 18. Right? Now, let me rewrite these as improper fractions so it'll be easier to match it against what's up here. So x1, the sum, ends up being 2 by 3, 6 plus 1. That's 7/2. This is 3 times 2, 6 plus 1, 7/3, and 18. Now, x sub 3 could be any real number, and that's cool. That's fine. X sub 1 could be any number. So this one is X sub 1, which is fine. It looks like that. It's not 0. X sub 3 is fine. It's a real number. But how about this one? Can I say 7/3 is 1 over x1, 1 over 7/2? That's not true, is it? 7/3 does not equal invert and multiply 2/7. See? They don't come out. And I pick positive numbers. You could have picked negative numbers, by the way. You don't have to go with this. There again, there you go. For this to have worked, it had to be in that structure. Whatever x1 is, this should have been the reciprocal of it. So this one, therefore, is not a subspace, not a subspace of R3. Is everyone okay on this work? So we are done, folks. We are done with this section. If you're okay, we're going to move on to the next section. We're cool. Okay, so let me switch to the page of the book and let's go to our next section. So hopefully now you feel a little more comfortable. It's kind of an abstract idea. I don't think you've done anything like this in your math lives so far. So that's good. It's a different take on what we do. Let's go on to next section, section 4.4. Now, in section 4.4, spanning sets and linear independence. So what we want to do in this section, call it our objective. Our objective is that we want to represent each vector in V, the parent vector space in V, as a linear combination of a select number of vectors in the space. That's called the spanning set. Okay, so that's what we want to do. So if you look at, for example, that's definition of linear combination. We defined what the spanning sets are in just a moment. But that's what we want to do again. We want to represent, again, the vectors in the vector space as a linear combination of other vectors in the space. That's what we want to do. So first, what do we mean by linear combination of vectors? It's simply what you see here. So let's say we have a vector V in the vector space V, remember, in the parent vector space. So this is a vector in there. And then this vector is a linear combination of other vectors, U1, U2, UK. These are all in V. So you have one vector in the parent set written as a linear combination of a bunch of other vectors in that same set. Then this is what the linear combination will look like. And there you go. Okay. So this is called the linear combination of vectors in the set. The C's here are constants, scalars. The boldface are vectors. So here you go. This is an example, actually. We can just view it. So in this example, he said, here's my set S. Okay. This is a set of vectors in R3. So he handpicked again. He selected 3 random vectors from that vector space. Vector 1, vector 2, vector 3. Now, it says vector V1. This vector is a linear combination of V2 and V3, right? Remember the linear combination? This vector V, right here, this vector V is in the parent vector space cap V. So are these U's. So all of these vectors are in V. We want to write one, in this case, he's choosing V1, one of them as a linear combination of the others. So V1, it says, is 3v2 plus v3. He's shown you that it works. So this vector is a linear combination of v2 and v3. That's all that is. Now, look at the matrices, 2 by 2 matrices. So he has 1, 2, 3, 4. Now remember, we're going to call these vectors. Even though they're matrices, they're called vectors. Because vectors, components of a vector could be numbers like 1, 3, 1. It could be like this. Those are components of a vector. It could be real numbers. Or the components of the vector could be objects. Could be objects, it could be matrices, it could be polynomials, it could be anything. So here he's choosing matrices, 2 by 2 matrices, so these are 4 of them. And it says one of those, the first one, is this linear combination of the other 3. And he shows you that it works. There you go. This is V1, exactly V1. By doing this is the linear combination. Okay. And it's called linear because you have V2, V3, V4. You don't have V2 squared or V3 squared, V4 cubed. These are linear. They're linear in these vectors. Okay. So that's what the linear combination means. Okay. Now, let me switch and actually show you my own example here. Okay, so in this example, and we are in section 4.4. Okay, so for this example, I'm gonna let's say I have one vector u is going to be 1, 2, -1. Okay, and then I have another vector, call it vector v. This vector, I made it to be 6, 4, 2. And then these are 2 vectors. These are in R3, right? In 3 dimension, because they have 3 components. So these are 2 vectors in R3. Now, is vector W, and my vector W, I made it to be 9, 2, and 7. Is this vector a linear combination of a U and V? So can I write this vector as a linear combination of these 2? Okay, so let's go through and try to do this. Well, if I can, according to the definition, doesn't that mean W has to be C1 U plus C2 V? This is the definition of linear combination. Means you have to be able to write it as some scalar multiple of the 2 vectors. Now, let's see how this is going to work out. So on the left, I have my W. W is 9, 2, 7. Will that equal to, is it possible for it to be equal to C1 times U is 1, 2, -1, plus C2, a different, possibly constant, could be the same, but possibly different, 6, 4, 2. Okay, now, from this, let's take a look at the right side, because the left side is just the numbers. Look at the right side. A constant multiple of a vector, so you distribute the constant to every component, right? In both. And then to add them, we add the first components, second components, and the last components, right? So the first component of the sum vector would be 1C1, that means just C1 plus 6C2. The second component is going to be what? It's going to be 2C1 and then plus 4C2. And the last component is going to be -C1. That's -C1 plus 2C2. Okay, so there you have those. Now, from this, we can actually set up a system of equations because in order, this is a vector, right, on the left. This is a vector on the right. Two vectors are equal if and only if each component of the vector on the left is equal to the component of the vector on the right side. So that means C1 plus 6C2 should equal 9, true? Because that's the first component on the left side. And then 2C1 plus 4C2 should equal to 2. And finally, negative C1 plus 2C2 is equal to 7. Now, note we have 1, 2, 3. And we have 3 equations, correct? 3 equations. And we have 2 unknown. Because we have more equations than unknowns. So that right there tells me that one is linear combination of the other. However, we want to actually find the linear combination. So this matrix, we're going to do Gauss-Jordan. And I used Symbol Lab, by the way. When you do Gauss-Jordan, this is what you should get. The first row is 1, 6, 9. Second row gave me 0, 1, 2. And what do you think the last row ended up being?
-1, 2, and 7.
Negative 1, 2, 7. That will give me another equation, right? Remember, Gauss-Jordan, we only have 2 unknowns, but I have too many equations. I really need only 2. And I got the 2. So what do you think this should be?
Would it be just all zeros?
You got it. There you go. It's all zeros. So that tells us that one of the equation is redundant. Now let's see which one. How can we write W as which specific linear combination of this and this vector? So now from the matrix, clearly the last row just says 0, 0, 0 means you just don't need that equation. You just need these two. Now remember, these are the coefficients on C1 and C2, right? These are coefficient on C1, C2. From the second equation, C2 isn't that 2? C2 equals 2. We just read this equation. This is the augmented matrix. So C2 is 2, and back substitute in here for C2. C1 is going to be 9 minus 6 C2, and that's going to be 9 minus 6 times 2, or it's going to be negative 3, isn't it? Okay, perfect. So this is what we're claiming now. I can write W as C1U. C1 is negative 3. So I can write it as negative 3U plus C2 is 2, C2 times V. It's going to be 2V. And there you have it. We are able to write again. W, this is the linear combination. Right there. There you have it. And because the solution to the system isn't that a unique solution, so the linear combination is going to be unique. That linear combination is unique because the solution is unique. Unless I have, sometimes the solution may end up being infinitely many, right? Then that means I can write these as different linear combinations. But for this one, because the solution is unique, this linear combination means only this combination works, nothing else works. Okay. So now let's take it, if you're okay, we'll move on. If you have question again, please feel free to interrupt me and ask. Now, let's take a look at another example similar to this one. So this was our example that we just did. Now, let's take a look at this other example. In this example, same kind of principle. Can I write W? And W, this time I picked 4, -1, 8. Can I write W? Can W be written as a linear combination of, now I'm going to go with the notation in your book. I'm going to this time call them U1, U2. Again, these vectors all belong to the parent vector space. So W is in V, the parent vector space in R3. This is in R3. And U2 I'm about to write is in R3. Any vector you write is going to be in R3. And this one, I'm going to go 6, 4, 2. Can this be written? Question mark. So let's try this one. Same principle as before. If it can, then I can write W as a constant multiple C1 U1 plus C2 U2. Again, this one is more intimate, the notation, with the one that was in the definition. So W is going to be 4, -1, 8. C1, C2 are to be determined. So here's C1, 1, 2, -1, plus C2, second vector, 6, 4, 2. Okay. Now let's add on the right side. C1 times 1 plus C2 times 6. That would be the first component of the sum vector. That's C1 plus 6 C2. And then 2C1 plus 4C2. 2C1 plus 4C2. That's the second component. The last component is -C1 and then 2C2, -C1 plus 2C2. And now let's see, in order for these two vectors to be equal, again, every component, the corresponding component must be identical. And they have to be identical. That means C1 plus 6C2 should equal to the first component on the left. 2C1 plus 4C2 should equal to -1. And -C1 plus 2C2 should be 8. So again, I have the case where I have 3 equations, 2 unknowns. Let's solve this and see what happens. So the matrix form of the system, 1, 6, 4. 1, 6, 4. The second row of the matrix is going to be 2, 4, -1. That is 2, 4, -1. The third row is going to be -1, 2, 8. Right? -1, 2, 8. And again, I ran this through Symbolab and did a Gauss-Jordan on this one, and look what it gave me. The Gauss-Jordan ended up being 1, 6, 4. Second row turned out to be 0, 1, 3 halves. So I got my ones on the diagonal. Check out the last row, 0, 0, -3. So what do you think? What does this third row tell you? Remember, these are the coefficients for the first column on C1, second column C2. That's the augmented matrix. This is what they equal to. So what does the third row now read?
We cannot have a linear combination.
You got it. This says 0 equal -3, doesn't it? And of course, that's not true. So this system is inconsistent. That means it has not a solution. It does not have a solution. No, so you cannot find a C1, C2 that works. Therefore, this linear combination cannot be done. Thus, W cannot be written as a linear combination of the two vectors u1 and u2. Let's see how that works, everyone. Are we okay on this example, ladies and gentlemen? Okay, I think we're good. So let me go back to the book. Wait, 45. We got 10 minutes here, folks. Let's make the most of it. Let's take a look at the page of the book. So again, hopefully everyone is okay on what we've done so far. Now, let's go to another definition. Okay, we're going to define spanning sets now. Okay. Now, here's the definition of what we mean by a spanning set. So a spanning set of the vector. The set S that's made up of vectors v1 to v2 all the way up to v sub k, okay, is a subset of the parent vector space. The set is spanning set when every vector in V can be written as a linear combination of vectors in S. Ain't that cool? So if we can find such a set, so remember, the parent vector space has a whole bunch of vectors in it, right? Infinite many, so many in there. If we can write, the keyword is every. If we can write every vector in the parent vector space as some linear combination of these vectors that are in this set S, then we say that the set spans V. Think of the span as coverage. It's going to cover the entire vector space. It spans it. Okay, so that means again, set S contains all vectors in the original vector space. Every vector in V in the original vector space can be written as some linear combination. So S, again, S itself is made up of these different vectors that are in V. But once you do different combination of them, that is capable of covering every vector in V. Okay, so that's just the definition. Now, let's go down here. And so what do we mean by span? Span of a set. Okay, so again, if S is a set of vectors in the vector space, the span of S, not V. Remember, S spans V, the vector space. That's what we set up here. See, set S spans V. It covers every vector in V. We're defining what the spanning of a set is now. So the span of a set is all linear combination of vectors in S. There you go. That's the span of S. It's all linear combinations in S. So remember, S had V1, V2, up to VK, right up here. Remember this part? V1, 2, up to K. All linear combination of these themselves, among themselves, is what's called the span of the set S. See, these are made up of VK. Now, the span of S, this is how they write it. And when span of S is equal to the vector space, then V is spanned by these vectors. S spans V. So this is kind of, see in the end, the conclusion, this is exactly what we said up here. Remember up here we said S spans V if every vector in V can be written as linear combination of these in this set. So if we can, let's say, define a subset and we can show the subset covers every vector in V, then it spans it. So that's what that is. That's the span of the set. So it's all possible linear combination of these, however many there are. Okay. Now, And the V's here, by the way, these subscripted V's, these V's could be row or column vectors. Okay, these V's could be row vectors or column vectors. Okay. Now, let's take a look at, let's see, and then span S is a subspace of V. That's a theorem. The span of S is a subspace of V, right? Because its linear combination of all the vectors in here are going to look like all the vectors in V. So they're going to preserve the structure that's in V. So that's what this says. Now, span S is the smallest subspace that contains S. So every other subspace must contain a span of S. So it's called minimal. So span of S is minimal, in other words. Minimal means it has the fewest number of linear combination of these vectors. So for example, all I need to do is combine V1, V2, and V5, and that will cover every vector in V, hypothetically. That's the minimum number of vectors that I need, V1, V2, V5, 3 vectors. Okay. Now, let's take a look at an example here, probably the best way to talk about this. So let me switch, and then probably by the time we get through this, we'll be done. We can stop here. Let me change my share, go to my notepad here. Okay. Let's take a look at this one now. So here's our example. This is in section 4.4 example. So in this example, here's a question. Determine whether making V1 to be 1, 1, 2. V2, another vector, to be 1, 0, 1. And V3, this other vector, let it be 2, 1, 3. So there you go. We got these 3 vectors. We want to know whether these vectors span the vector space in R3. Whether these span the vector space in R3. In other words, can I write every vector in R3 that are in the form A, B, C, anything you can imagine as a linear combination of these 3? Okay, so let me do this now. If we could, then remember, these are the vectors in V, correct? These are vectors in V. So let me write these. I'm going to write them as, let me change to B1, B2, B3. Because if I go A, B, C, and then here I'm going to have C's, and there will be a conflict. But would you agree this is the form of the vectors in R3, the general vectors? Any vector you can think of, it will be in this form. Like this could be pi e square root of 2. There you go. That's one of them. Is this, can this be written as C1, 1, 1, 2, plus C2, 1, 0, 1, plus C3, 2, 1, 3? Right? That's what we want to know, just like the previous one. Now, if I write the right side, in the right side, you combine the first component. So I'm just going to write it. It's going to be C1, C2, plus 2C3. The middle one is going to be C1. 0 C2 is C2. 0 times anything is 0. 1 times C3 is C3. And the last component is 2C1 plus C2 plus 3C3. Right? So that's that linear combination. Now, we can set up our system, right? The system, first component equal to that. C1 plus C2 plus 2C3 equal the general form B1. The middle one, C1 plus C3 equals B2. And the last one is 2 C1 plus C2. Oh, sorry. No, yeah, no, I'm not sorry. It's 2C1 plus C2 plus C3. 3C3 equals B sub 3. Right? Oh, please check. I think that looks right. So first component first, second, third. Okay. Now, here's a system, right? This system is in the form, the general form AX equals B, isn't it? Like the one that was on your exam, remember? The general system, that's in this form. Instead of X, I have C, a matrix of coefficients are C. So the question we want to ask is this: is the system of equations that we have, is the system consistent? In other words, does it have a solution, right? We want to know if that system is consistent. So, how do we determine that? Well, what is the condition for consistency? Remember, we had a whole bunch of equivalent statements. One of those equivalent statements we had about a matrix, about this, and the inverse of a matrix, A inverse, right? Well, condition for consistency, that means non-singular matrix, is that if this is consistent, what do we know about the determinant of A? If system is consistent, what should the determinant of A be? Can it be 0? If determinant is 0, that means the matrix A is not invertible. If it's not invertible, I cannot solve for X. So the condition says the determinant cannot be 0 for this system to be consistent, right? So let's check out the system. My system, we're talking about A here. A is the matrix of coefficients. The coefficients are 1, 1, 2. 1, 1, 2, 1, 0, 1, and 2, 1, 3, right? And the determinant of this, if you try this, the determinant of matrix A, call this matrix A. A is a matrix of these coefficients. The determinant is 0. You can verify that. I ran it through Symbolab. And there you go. The determinant is 0. So that means A, matrix A, is singular. Singular means it does not have an inverse, right? So one row is linear combination of another row. So what's the conclusion? The system is not consistent. Therefore, the three vectors, v1, v2, v3, do not span R3. I cannot write every vector in this form in R3 as a linear combination of only these three. So that's the upshot of this. Now, real quick, and we're done, folks. I know it's time to go. Give me 1 minute, I promise you. Let me just put a note here. When I did the Gauss-Jordan on this matrix A, this is what it looked like. I got 1, 0, 0, 0, 1, 0, 1, 1, 0. Right? Which means, because I have a row of zeros here, I have a row of zeros here. So that tells me that this implies A, matrix A, this matrix of coefficient, has only 2 independent vectors. In other words, this one of these vectors is itself is linear combination of the other two. One of these vectors is linear combination of the other two. It has only two independent vectors. To span R3, it needs exactly three independent vectors. So there you have it. So this is not going to do it. I will not be able to write every vector in V using these three. Now we'll look at the cases later on where this will be definitely doable. We will be able to do that, but not with this example. Okay, and we passed 9 o'clock. So let me stop the share and then see if there are any questions, and we'll wrap things up. So